Categorical propositions are propositions which claim a particular relationship between two categories or sets. And there are four standard categorical propositions. So notice that we're going to have a form. Those are going to be like the four different types. Then we're going to give an example to contextualize each. And each example is going to have a subject and a predicate denoted by S or P. So let's start with this example. All whales are mammals. So the subject set, whales, and the predicate set is mammals. And the form is that all of the subject are part of the predicate. All S are P. The next form is that no stationery is clothing. And stationery being like pencil and papers and things that you would do to write a letter in old-timey ways. So no stationery is clothing. The subject is stationery, like, letters, paper, pencils, all that stuff. And the predicate set is clothing. So this form is that no SRP, none of the subject set is belonging to the predicate set. Some police are dogs. So our subject set, police, our predicate set, dogs. And so this is saying that some police are dogs. Some of the subject set belongs to the predicate set. So some SRP. And then lastly, some gymnasts are not short. And so gymnasts are the subject set. Short people are the predicate set. So the form is that some S are not P. And this is definitely weird, and you might be asking yourself, like, why would I do this? But I think we can contextualize this further by looking at it in terms of a Venn diagram. So let's look at the forms, all four of them, in terms of like how they relate spatially to each other. So if we say all S are P, that means that all the whales, all the S set is inside the predicate set mammals. So this is like the egg with the yolk situation. So you've seen this before with Venn diagrams, where S is actually a proper subset of P. In the next case, no S are P. They don't share anything in common. So this would be your disjoint sets where they don't touch. Some S are P. This is telling us that there is some shared there are some shared elements. There's something in common. They overlap a little bit, but not completely. So this is going to be a Venn diagram with overlap. And we're actually talking about the space that they share, where that red X is where the overlap is. And then some S are not P. This is the same setup. There is some sharedness, but we're not looking at that particular region. Now we're looking at the region of S that is not shared by P. And in the past, we've talked about this as S only, or S but not P, or S and P complement. So those are things that hopefully are bringing you right back into our lecture about Venn diagrams because they're so fun. So here's an example. The premises are all cats are mammals and a tiger is a cat. And so what we're going to do is we're going to validate an argument using Euler diagrams. So this case is all S are P. And the conclusion is a tiger is a mammal. Okay, so how are we going to use this? We know we're all S are P. That's our form. And it says, so that's like the first premises. All cats are mammals. So we've got our setup. And now the second thing says a tiger is a cat. So cats that's the set S, that's our subject. And mammals, that's our P set. So we need to figure out a tiger is a cat. That means I'm in the set of cats. I'm here with the red X. Does that mean that I'm also in the mammal set? Yes, I cannot be in this set of cats without being in the larger space of mammals. So in this case, the argument is valid because that X, where the tiger is, must therefore fall within the mammal set. Validated. All right, next examples. All firefighters know CPR. So again, we've got S and P. Firefighters are S. P is people knowing CPR. Then we also have that Jill knows CPR. And we want to know if we can conclude that Jill is a firefighter. So for the firefighters, we need to figure out, can we put that Jill, we want to like place Jill somewhere. Do we place her in the firefighter circle or not? Do our premises support that Jill would be in the firefighter circle? And I claim that you can't tell. So when you can't tell, she might be a firefighter, but we don't know for sure. What you do is you mark an X on the boundary, and that indicates like your lack of certainty here. And so you could not actually validate this argument because we don't have enough information. And you can think about that contextually. If there's anyone here listening that has ever been certified and knows CPR, you can ask yourself, well, am I also a firefighter? Some of you might say yes, and some of you might say no. Like I've been certified for CPR and I'm absolutely not a firefighter. So it doesn't necessarily mean that you're a fighter just for knowing CPR. Here's another one. If it has an engine, I can fix it. Cars have engines, so I can fix cars. And so this is an all SRP situation again. We've got things with engines encompassed in the things that you can fix or I can fix. So now we need to figure out where cars are. They're in the things with engines. And so does that fall within the larger circle of I can fix cars? Yes, it does. This argument is valid because the X must fall in that larger circles of I can fix it. Another example here, all children are energetic. Some actors are children. So this is some SRP. And then we need to figure out if our conclusion is valid. The conclusion is some actors are energetic. So here we're going to be some SRP. And we've got children. All children are energetic. So children belong in the energetic circle. And then some actors are children. And so here we have an overlap where not all actors are children, certainly, but there is some overlap. So can I conclude that some actors are energetic? Sure, that would be in that overlapping space. Like there is a place for those actors to be energetic. And so this argument is valid. Some of the actor bubble falls within the energetic set.